This is the second video about distributions, and we're continuing along with the shape of distribution, but this is of course part 2. So let's start with the shape of a distribution. And if we think about the shape of a distribution, we can abstractly describe it as a density function, where again this is the value of x and this is the probability of x. So the height talks about what the probability of a given value of x is. And let's say we had a distribution that looks like this. And if you notice, we can read some things about this distribution, right? That it's more likely to be in this region. Though you do have some values of x that are very large, which are possible. So large values here of x are possible, but unlikely. And this is actually the generalized shape of U.S. income, right? If you think about U.S. income, what we have is, if this is the actual value of income, what we notice is that there are some people that make very little income. Then there's a larger proportion of people that make a higher amount, but not a great amount. And as income rises, the number of people having that gets less and less, and eventually becomes very small. But there continue to be people that make very high incomes. And one way to think about this is just a histogram that's been generalized, if that's the way you want to think about it, right? Let's let this be x here, and this be the probability of x, right? So this could be income. Then what you could think about is a series of histograms where each histogram, each width of each category is equal, but not the same number of people are in each category. Etc. Dot, dot, dot. Right? It's just an old-fashioned histogram, right? Where the height of, say, falling in this particular category, this might be, for example, but the value of income between, say, $48,000 and $55,000. And the way you read it is you read across to see what the probability of falling within that category is. Now, if you think about it, you could draw a generalized curve here, which might not capture exactly, but will roughly capture this relationship, and that's your density curve. So you think about the density curve is simply the limit of histograms is the number of columns or the width of the columns. Either the number of columns goes to infinity or the width goes to 0. Continuous histogram shape. Well, when we get that, then we can find out some simple examples. So the first idea is we can find the idea of a symmetric distribution. And the way to think about a symmetric distribution is compare it to the mean. So I'll just freehand this so it won't be perfect. But if this is your mean value, if you have roughly a distribution which is more or less equal on each side of the mean, then that's called symmetric. Sometimes symmetric around the mean. It can be really wide or it can be really narrow. That doesn't necessarily matter. Just whether or not it has the same shape. And you can also have something called a uniform distribution, which is that all likelihoods are equally likely. Right? This is always x, and this is px. In this case, this will be the mean. In this case, this will be the mean, and this is the mean. And what symmetric means is that the graph looks roughly similar on each side of the mean, or are roughly symmetrical. or mirror images. You can think of that's another word for symmetrical. They're roughly mirror images across the mean. And I'm sorry, I'm not sure if that's the way you spell across or if there's two C's. We'll have to think. That's symmetric. Then you have something called skewed distributions. And a skewed distribution is not symmetric across the mean. And in particular, then you can have a skewed distribution that looks like this. Another one could actually look like this. Or let's do one more. And all these are called skewed to the right. And if you notice all of these, if you calculate what the mean is going to be, I'll just eyeball it here, so we're not exactly sure, but the mean should be roughly there, roughly here. This one would probably be here. Then in some cases it's not symmetrical across the mean, and the question is if there's a longer tail, which is usually when we talk about skewed, there's a longer tail, is the longer tail to the left or to the right? And that's how you tell if it's skewed to the right or the left, is where is the longer tail? And let's do skewed to the left. Skewed to the left could look like this. It could have a fixed value where it doesn't get beyond, right? That's possible. Or it could even look fairly symmetrical, but just have one tail that's much longer. Right? So all of these skewed to the left. Here's kind of a truncation or a max value. Right? And in some sense, if you notice all of these, the longer tail is to the left, right? I'm sorry. Yeah, the longer tail is to the left. So that's the longer tail. There's the longer tail, and there's the longer tail. That's why we call it skewed to the left. In addition to skewed distributions, there's another distribution which is called a bimodal distribution. Now, mode is an odd idea. Mode is an idea that you always study to pass your high school X exam, and then you never really use it, and this is the one instance. So let's look at what bimodal means, right? Bimodal might look something like this. Right? In that case, what you do is you have, sometimes it's called two-peat. Right? And in some sense, what you have, if this is x and this is p of x, then there are two values of x that are more likely. You might imagine this if you're thinking of politics. You're going to ask someone a question about what their opinion of is Mitt Romney or Barack Obama on a scale from 1 to 10. And you might have a lot of people that give a really high and a really low ranking. So let's x be your ranking from a scale from 1 to 10, and let this be 2 and this be 8, and this be the probability of each. And then you could imagine a situation if this is a fairly popular candidate. There's a lot of people who like him a lot, and a lot of other people who really don't like the candidate. And there could be people spread out in between, but in this case there's two modes, bimodal. So what's the opposite of bimodal? You could think of it unimodal, but sometimes we call it unipeat or single-peat. Probably single-peat is a better example. So all of the previous examples, Skewed to the left, skewed to the right, and symmetric are all examples of what we call single peaked. So what do we have here? We have symmetric, and we have skewed to the left and to the right. And then you have bimodal. I think it's a matter of taste whether or not you put in the dash or not. The one might be more correct. And usually instead of saying unimodal, we usually say single peaked is the alternative, right? So you have symmetric versus skewed, single peaked versus bimodal. And that's the second part of distributions, shape.